Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Algebra 1 and 2 class. Today we're going to be talking about fractions, decimals, and percents, part 1. There's a lot of stuff involved with fractions, decimals, and percents, so I'm going to break this up into two different parts. But in order to truly understand how to work with fractions, you have to realize that fractions, decimals, and percents are all different ways of writing the same value or the same exact number or fraction. Fractions, decimals, and percent values are all parts of a whole. Okay? Fraction, decimal, and percent values are all parts of one whole. So for example, the fraction 3/4 can be converted into 0.75, the decimal value. It can also be converted to 75%. So 3/4, 0.75 or 75 hundredths, and 75% are all the same exact value. They just have a different appearance. One is in fraction form, one is in decimal form, and one is in percent form. But other than that, they're exactly the same. So today, we will learn how to simplify and find equivalent fractions. And we're also going to learn how to read and round decimals. So let's get started. In order to work with fractions, decimals, and percents, we have to go over some basics, though. First of all, what is a fraction? A lot of people don't really understand what a fraction is. But fractions, very simply put, are simply part of one whole. And they are written as follows. Numerator in the top, denominator in the bottom. Okay? Numerator in the top, denominator in the bottom. The fraction 2/5 is read as 2/5 and represents 2 out of 5 pieces, which makes one whole. That's why it's called 2/5. Okay? It's 2/5 because it's 2 out of 5 pieces. So in this particular case here, I have 1, 2 pieces out of the 5 pieces that make up this pizza pie, and that is known as 2 out of 5 or 2/5. Okay? Pretty cool. That is what a fraction is. Again, it's part of one whole. Okay, so let's continue now. Let's take a look at what factors are. Factors, simply put, are numbers that go into other numbers evenly without a remainder. Factors are always less than or equal to the original number. For example, the factors of 20 will be, if I have 20 here and I want to find the factors, you start from the beginning. 1 times 20. 2 times 10. 4 times 5. And that's it. 6 does not go into 20. 7 does not go into 20. 8 does not go into 20. So simply, literally, factors are numbers that go into another number evenly. So I wanted to make this a little bit nicer now. Let's go ahead and we can write them all now as 1, 2, 4, 5, 10, and 20. And those are the factors of 20. Okay, prime number. What's a prime number? Well, a prime number is a number whose factors are 1 and itself. So prime numbers would include the only even number 2, 3, 5, 7, 11, 13, 17, etc., 23. I can keep going forever and ever, okay? There's a lot of prime numbers. But prime numbers are numbers whose factors are only 1 in itself. There are no other factors of that number besides 1 and itself. Now that we mentioned the number 1, I do want to note that 1 is neither prime or composite, which is a number who has more than 2 factors. So a composite number is a number that has more than 2 factors. A prime number is a number whose factors are only 1 and itself. And the actual number 1 is neither prime nor composite. It is not prime because it only has 1 factor, itself. And a prime number has exactly 2 factors. It's not a composite number because composite numbers have more than 2 factors, and the number 1 only has 1 factor, which is itself. So 1 is neither prime or composite. To go ahead and really focus on composite a little bit more, composite number again is a number that has more than 2 factors. So composite numbers would be numbers such as 4, 12, 80, 16, 9. All of these numbers have more than 2 factors. Okay? And that's what defines a composite number. Now, there's a skill called prime factorization that is very important. And prime factorization is the process of breaking down a number into its primes. For example, the prime factorization of 24 is, let's take a look at it. If we have the number 24, and I want to find the prime factorization of this number, that means that I'm going to break this number down into its prime factors. So we can start with any combination that you want to start with. I'm going to start with 6 and 4, because 6 times 4 is 24. Neither of these are prime, so I must continue to break it down. 6 breaks down into 2 times 3. Both are prime. Get into the habit of circling the primes. And 4 breaks down into 2 times 2. Get into the habit of circling the primes. That way you know who to work with. So now that we've broken 24 down into its prime factors, we can write the prime factorization, which is 2 times 2 times 2 times 3, or 2 to the 3rd power times 3. I use 2 to the 3rd power to note that there is a multiplication of 2 times itself 3 times. Okay? We will have a whole lesson on exponents, but briefly, exponents describe repeated multiplication. So 2 times 2 times 2, you multiplied 2 times itself 3 times. That's why I wrote 2 to the 3rd power. Okay? So the prime factorization, again, of 24 would be 2 to the 3rd power times 3. And that's it. Please do not multiply those. If you multiply those together, 2 cubed is 8, times 3 is 24. You go back to the original number. But the prime factorization is simply 2 cubed times 3. And that is a prime factorization of 24. This skill will be useful a little bit later on. A multiple. What's a multiple? Well, multiples are products of 2 whole numbers. Multiples are always greater than or equal to the original number. For example, the first 5 multiples of 4 are, well, it's the products of whole numbers. So the multiples of 4 are going to start with 4 times 1, which is 4. Then 4 times 2, which is 8. 4 times 3, which is 12. 4 times 4, which is 16, etc., etc., etc. Actually, I said 5, so 4 times 5 is 20. Let's do another one. 4 times 6 is 24. ... You keep going on forever, okay? So if you want to find the multiples of any particular number, take that number and multiply with all of the natural numbers, starting with 1. Okay? That's what a multiple is. Multiples are pretty useful, pretty powerful. So please make sure you understand that. Number 6. A greatest common factor. We already talked about factors, but now we're going to talk about greatest common factors. And a greatest common factor is the largest common factor between two or more numbers. If you know your multiplication tables and divisibility tests for numbers, it is very easy to find the GCF of two or more numbers. Now I'm going to help you out here, okay? I want you to be able to recognize factors quickly. And in order to do that, it's important to know the divisibility test, as shown below. So, the divisibility test is just a nice, easy way to recognize what numbers go into what other numbers. It makes your life a lot easier when you're simplifying fractions, finding equivalent fractions, a whole host of uses for this. So, a number is divisible by, that's this column down here, okay guys? So a number is divisible by one of these numbers if, and then we're going to fill in the blanks as to the restrictions to how it is that one number is divisible by another. So, a number is divisible by 2 if the number is even. If the number ends in 0, 2, 4, 6, or 8, it is divisible by 2. So 12 is divisible by 2. So is 384 because it ends in an even number. Okay? If it ends in a 0, 2, 4, 6, or 8, it is divisible by 2. A number is divisible by 3 if the sum of the digits is divisible by 3. So for example, the number 27. We know it's divisible by 3, but why? Well, 2 plus 7 equals 9, which is divisible by 3, so 27 would be divisible by 3. What about if we have 1,507? Well, 1 plus 5 is 6, plus 7 is 13. So the sum of the digits is 13. And that is not divisible by 3, so 1,507 would not be divisible by 3. What about 3,120, let's say, 3? Well, we've got 3 plus 1 is 4, plus 2 is 6, plus 3 is 9. So that means that since the sum of the digits is divisible by 3, then the whole entire number is divisible by 3, and that would work. 4. A number is divisible by 4 if the last two digits of the number are divisible by 4. So what ends up happening here is, if you look at a large number, this works really well for large numbers in particular. Let's say I have 3,048, okay? And I want to know if it's divisible by 4. Well, I look at the last two digits. Since the last two digits here are 48, and 48 is divisible by 4, then 3,048 is divisible by 4. 5. 5 is an easy one. A number is divisible by 5 if the number ends in a 5 or a 0. So literally, any number, no matter the size, if it ends in a 5 or a 0, it is divisible by 5. So 2,675, it ends in a 5, it's divisible by 5. 26,130, well, it ends in a 0, so it's also divisible by 5. A number is divisible by 6 if the number is divisible by both 2 and 3. Let's look at an example here. Let's look at the number 314. Okay. 314 is divisible by 2 because it is an even number. It ends in a 0, 2, 4, 6, or 8. So it is divisible by 2. That works. And then if I look at the rule for 3, 3 plus 1 is 4, plus 4 is 8. Now this will not work. Okay? That is not going to work because it has to be divisible by both 2 and 3. So how about this? How about 180? Well, 180, 2 is divisible, right, because it's an even number. It's 180. And if you add the sum of the digits, you've got 1 plus 8, which is 9. 9 is divisible by 3, so 180 is divisible by 6. So again, a number is divisible by 6 if and only if the number is divisible by both 2 and 3. A number is divisible by 9 if, very similar to the 3 rule, if the sum of the digits is divisible by 9. So why don't we take the number 270. 2 plus 7 is 9. That's divisible by 9, so 270 is divisible by 9. And 10, a number is divisible by 10 if the number ends in 0. So any number that ends in 0 is also divisible by 10. Okay. Now, equivalent fractions. Equivalent fractions are fractions that have the same value with a different appearance. It's that simple. In order to find equivalent fractions, simply multiply or divide the same value to both the numerator and denominator of a particular fraction. When you divide by the same value, you are reducing the fraction to lowest terms, just so you understand that. So for example, I want to find 3 equivalent fractions for 3/5. So I am literally and simply going to multiply the same number to both the numerator and denominator. So I'm going to make my life easy. I'm going to to find my first equivalent fraction, I'm going to multiply 3/5 by 2 over 2, which gives me 6/10. So 6/10 is an equivalent fraction for 3/5. But guess what? Since 6/10 is already equal to 3/5, I can multiply that by another 2 over 2, giving me 12/20. Okay? And I could keep going like that forever. Or I could start with my original 3/5, and this time, let's say I want to multiply by 12 over 12. Well, this will give me 36/60, which again is my third equivalent fraction to 3/5. Because you simply have to multiply or divide the same number to both the numerator and the denominator. Okay? I could not divide anything from 3/5 in this case, of course, because they're both prime numbers and I can't divide anything out except for 1. Now, when we're reducing a fraction, for example, I ask you here to reduce 24/40 to lowest terms. In this case, I have to divide. I have no other choice because I want to reduce it to lowest terms. So it's very simple. I go ahead and take my 24/40 and using divisibility tests and just multiplication facts and knowledge, I ask myself, okay, what number goes into 24 and 40? Well, I know that the largest number is going to be 4. Very simple one. But let's just say you didn't. You do know that 24 is even, right? And you do know that 40 is also even. They both end in a 0, 2, 4, 6, or 8. So you could start by dividing by 2 over 2 to both top and bottom, giving you 12/20, which are both still even. So I could still take out another 2, giving me 6/10, which again I could divide another 2, which gives me 3/5. Okay? 3/5. So actually, the best and easiest way to do this is to recognize that 24/40, you can divide 8 to both top and bottom. You can divide 8 to both top and bottom because 8 is the greatest common factor of both 24 and 40, and that gives me 3/5. If you could recognize the GCF right from the bat, or from the get-go, it's a lot easier because all you have to do is just divide the numerator and denominator by that GCF, and you're done. If not, go the long way. I promise you, with enough practice, you will get very good at this and very quick. Okay. Least common multiple. Well, the least common multiple is the smallest common multiple between 2 or more numbers. If you know your multiplication tables, it's easier to find the LCM. Okay? For example, I want to find here both the GCF and the LCM of 18/30ths. Now, in this particular case, it's not so easy to find the LCM. Okay, the GCF, it's pretty easy. The GCF here is going to be 6, but that's not really going to help me for my multiples. So when you don't know the common multiple, the LCM, right off the bat, I'm going to show you a little trick. Go ahead and break down each of the given numbers using your prime factorization. So 18 breaks up into 2 times 9, circle your prime, and then 3 times 3, circle your primes. 30 breaks down into 3 times 10, circle your primes, 2 times 5, circle your primes. Okay, so now you have the prime factorization for both 18 and 30. Now I want to find my GCF. All right, this is very simple. In order to find my GCF, look at both prime factorizations. When you find a pair of numbers, okay, one being on one side and one on the other, a pair, you pull that pair out as one of that value. So for example, on my left side here with the 18, I have a 2. But on the right side where the 30 prime factorization is, I have another 2. So a 2 and a 2 comes out as 1, 2. Next, I have a 3 on the 18 side and a 3 on the 30 side. So a 3 and a 3 comes out as a 3. Do I have another 3 on both sides? No. Do I have a 5 on both sides? No. So my GCF is simply 6. Every pair of matching numbers comes out as one of that value. Now, to find my LCM, I'm literally going to take my GCF times all the left over prime numbers. It's that simple. So my LCM in this particular case would equal my GCF of 6 times my leftover prime of 3 times my leftover prime of 5, which would equal 6 times 5 is 30 times 3 is 90. And that, my friends, is the LCM. Okay? If you have to, go ahead and pause, rewind, and watch that again. But this is a very important skill. Okay, least common denominator. Well, least common denominator is the least common multiple of the denominators of a set of fractions. It's the least common multiple of the denominators of a set of fractions. In order to convert fractions into a fraction with the same LCD, one, you want to go ahead and find the LCD. Number two, you want to convert the given fractions into equivalent fractions with the chosen LCD. And we already went over equivalent fractions. In order to find equivalent fractions, all we have to do is multiply both the numerator and denominator by the same exact number. So for example here, find the LCD of the given fractions, then convert each fraction using the LCD. Well, I'm going to go ahead and look at 12 and 15 here. This is where knowing your multiplication tables really comes in handy. The LCD here, for sure, is 60. Okay? Now I know that because I've been doing this a long time and I know my multiplication tables very well. Let's just say you didn't. Well, worst case, go ahead and split them up. You got 12 and 15. 12 is 2 and 6. 3 and 2, remember to circle the primes. You got 3 and 5. That's a prime, that's a prime. So my GCF would be, you got a 3 and a 3, so that comes out as a 3, and that's it. you may say, hey, wait a second. Don't you have 2 2s? Yes, I do. But I have 2 2s on the same side. Okay? 2 2s on the same side do not come out as a GCF. But I did have a 3 on both sides, so that came out as a GCF. Now my LCM is the product of my GCF times my leftover primes. So I have 3 times a 2 times another leftover 2 times a leftover 5. And that is 3 times 2, which is 6, times 2, which is 12, times 5, which is 60. So this prime factorization, I know it's a little tedious, but it's very powerful. So I know now that my LCD, this is my first step, find it, is 60. Now I have to convert each fraction to have the denominator that is equal to the LCD of 60. So I've got 5/12. Well, I've got to convert 12 into 60. How do I do that? Oh yeah, I can multiply 12 times 5 to give me 60. But if I multiply something to the denominator, I must multiply it to the numerator because I am creating equivalent fractions. Okay? I'm changing the appearance, but I'm not changing the value. So when I multiply 5/12 by 5 over 5, I get 25/60ths. And 4/15ths, well, what do I do to 15 to get to 60? Well, I multiply by 4. And if I multiply 4 to the denominator, I must multiply 4 to the numerator. So 4/15ths becomes 16/60ths when I have an LCD of 60. So 5/12ths becomes 25/60ths, and 4/15ths becomes 16/60ths. And just so you know, this is coming in a little bit, but now you would be able to add or subtract these fractions because they have the same common denominator. But we'll talk about that in a little bit. Okay, now let's move on to decimals. Let's talk about rounding decimals, okay? In rounding decimals, I'm also going to teach you how to write decimals, so we'll have a little simultaneous lecture here. I have this number, 9,605,872 and 145,673 millionths. So check that out. I had 9,605,872. Okay, got to follow the place value. Okay, place value not only works for whole numbers, but it also works for decimals. So the 9 is in the 1 million spot, so that's why it's 9 million. 6 is in the 100,000s. Okay, notice that it's thousands with an S at the end. So that's 9,605,000. 6 is in the 100,000s, 0 is in the 10,000s, 5 is in the 1,000s. 9,605,000. 8 is in the hundreds, 7 in the tens, and 2 in the ones. 9,605,872. Decimal reads as and. Okay, so that's why I said 9,605,872 and. Now, when you're reading decimals, you read the number by itself according to its value, and you end with the place value. So forget about this decimal for a second. This number by itself is 145,673. But where does it end? It ends in the millionths. Notice that to the right of the decimal, to the right of and, you have the endings in THS, THS, THS. You have the tenths where the 1 is. You have the hundredths, THS, where the 4 is. You have the thousandths, where the 5 is. You have the 10,000ths, where the 6 is. You have the 100,000ths, where the 7 is. And you have the millionths, where the 3 is. So again, you read that decimal normally. Okay, you just read it as if there was no decimal at all. And you end with the last place value of that number. So this is 145,673 millionths. Why? Because the 3 is ending in the millionth spot. So one more time, this whole number would be read as 9,605,872 and 145,673 millionths. Rounding decimals, okay? I'm going pretty fast because I know that you guys have learned this before, all of you ladies and gentlemen out there in the internet world. I know you've learned this before, but I just wanted to give you just a little refresher. In order to round decimals, follow the same procedure as rounding whole numbers. Well, you may say, I kind of forgot how to round whole numbers. Well, no worries. You round whole numbers and decimals the same exact way, using the same procedure. Okay? And that procedure is as follows. Number 1, find the place value you're rounding to. Pretty simple. They're going to tell you, round to the nearest tens, or round to the nearest hundredths, or round to the nearest 100,000s, or round to the nearest 10 millionths. So find the place value you're rounding to. And then number 2, you're going to go ahead and look at the number to the right of the number being rounded. If that number is less than 5, then the number being rounded stays the same and every number to the right of it drops. If that number is greater than or equal to 5, then the number being rounded goes up by 1 value and everything to its right drops. So for example, let's do a few. Round each number to the given place value. Okay, I want to round 0.14 to the nearest tenths. Well, I'm first going to find the tenths. Okay, sorry about that. First going to find the tenths. And the tenths here is the 1. I'm going to look at the number to the right of the tenths, which is the 4. That number is less than 5, so this tenths stays the same, and the number to the right of the number being rounded drops. So this will equal 0.1. The 1 stayed the same, and the 4 dropped. How about number 2? Let's round 1.397 to the nearest hundredths. Well, let's locate the hundredths. Tenths, hundredths. The hundredths is right here, the 9. I'm going to look at the number to the right of the value I'm rounding. It's larger than 5, so 9 is going to go up. But I did this on purpose. If 9 goes up, it becomes 10. Well, where does that 1 go? Well, that 1 carries over to the 3. 1 plus 3 now is 4. So I have 1.40 as a rounded number to the nearest hundredths now. How about number 3? Round 690 and 3 thousandths to the nearest hundredths. Well, we look at the hundredths again. Tenths, hundredths is my 0. I look to the right of the number being rounded to see if it's greater than or equal to 5 or less than 5. In this case, it's less than 5. So that number drops. The 0 stays the same. And my answer will simply be 690 in this particular case. How about 14 and 3,983 10,000ths? I want to round this to the nearest thousandths. Well, I first find the thousands, tens, hundreds, thousandths. It's my 8. I look to the right of that number. If it's 5 or greater, it goes up and everything to the right of it drops. If it's less than 5, it stays the same and everything to the right of it drops. In this case, 3 is less than 5, so that drops and the number stays the same. And that's it. You have it in a nutshell. Thank you very much. I hope you learned a lot and have a great day. Bye-bye.